Hi everyone. Welcome back to the Symphonics series on building a BACnet stack. In Ep02, we created the BACnet data link layer as a separate module, making it easy to switch between transport types like BACnet IP version 4, v6, Secure Connect, or MSTP, while keeping the upper BACnet logic unchanged. In this video, we'll focus on BACnet IPv4 over UDP using the W5500 chip. We'll break down the packet structure from Ethernet, IP, UDP layers to BVLL, NPDU, and APDU, and show which layers are handled by W5500 and which we implement in firmware. Alright, let's talk about the BACnet datalink BIP4 module. This module handles sending and receiving BACnet IPv4 messages over UDP using the W5500 Ethernet chip. First, for receiving messages, we have the function BACnet datalink BIPv4 receive NPDU. So, what does it do? It listens for incoming UDP packets from the W5500. Then, it decodes the BVLC layer to extract the NPDU. Next, it copies the NPDU into a buffer you provide, and fills the BACnet source address with the sender's IP and port. And of course, it handles timeouts and error cases. Now, for sending messages, we have datalink IPv4 send NPDU. Here's how it works. First, it encodes your NPDU into a BVLC frame. Then, it extracts the IPv4 address and UDP port from the BACnet destination address. Finally, it sends the frame through the W5500 UDP socket. If all goes well, it returns the number of bytes sent. Otherwise, it returns an error. So, together, these functions let your MCU communicate reliably over BACnet IPv4, handling the network layer with W5500, while we implement the BACnet layers, BVLL, NPDU, and APDU, in firmware. In the next part, we'll dive deeper into implementing the BVLL layer itself, so you can see exactly how BACnet messages are wrapped and prepared for sending over the network. Alright, let's take a moment to look into a BACnet IP packet. At the network level, we have the Ethernet frame, IP header, and UDP header. These layers are all handled by the W5500 chip. So, what does the chip do? It takes care of MAC addresses, IP addresses, and ports. It also handles checksums and packages the data into proper Ethernet frames. From our side, we just provide the payload, the actual BACnet data, to the chip, and it handles all the network transmission in big endian byte order. On top of that, we have the BACnet specific layers, BVLL, NPDU, and APDU, which we implement in firmware. BVLL, the BACnet virtual link layer, defines the message type, like unicast or broadcast, and includes metadata such as packet length. NPDU, the network protocol data unit, handles routing, versioning, and control flags. APDU, the application protocol data unit, contains the actual BACnet application data, including services like who is, I am, read property, or write property. So, by following the big endian format, both the chip and our firmware ensure that all devices on the network interpret the packet data correctly. Let's start with BVLC, the BACnet virtual link control. This file, BVLC BIPv4, C, provides a minimal BACnet IP BVLC interface for IPv4. It helps encode and decode BVLC frames for basic BACnet communication. Specifically, original unicast NPDU 0x0A, original broadcast NPDU 0x0B. It sits above UDP IPv4 and below BACnet NPDU APDU. Simply wrapping or unwrapping NPDU bytes without inspecting them. How to use it? Send. Build your NPDU APDU. Call BVLC encode. Then send via UDP port 47808. Receive. Read UDP datagram from port 47808. Call BVLC decode. And pass NPDU to the NPDU layer. This minimal implementation excludes BBMD and foreign device functions to keep it simple. But they can be added later. It handles big-endian BVLC lengths and supports broadcasts to the subnet. Alright, now let's take a look at the BVLC decode function. This function is used to unwrap BACnet IP frames and extract the NPDU inside. So, here's what it does. First, it checks the input frame and output pointers to make sure nothing is null. Then, it validates the minimum header length and makes sure the frame has the correct BVLC type. Next, it reads the BVLC length in big-endian format and verifies it matches the datagram size. It extracts the BVLC function code, for example original unicast or original broadcast. Finally, it provides a zero-copy view of the NPDU, pointing directly into the received frame. So we don't need to copy data around. If everything checks out, it returns BVLC OK. Otherwise it returns an error code if the frame is malformed or unsupported. This function is essential for parsing BACnet IP packets and hands the NPDU off to the next layer for processing. Alright, so now let's move on to the BVLC encode function. This is the part that prepares our BACnet IP packet before sending it out over the network. Basically, this function wraps the NPDU into a full BVLC frame, so it's ready to be transmitted over UDP. First, it checks the input parameters. If the output buffer isn't valid, we immediately return an error. Then it calculates the total frame length, which is 4 bytes of BVLC header plus the NPDU payload. If that total size is bigger than the output buffer, we return an error because there's not enough space to build the frame. Next, we start writing the BVLC header. The first byte is the BVLC type, always 0x81 for BACnet IP. The second byte is the function code, like unicast or broadcast, and the next 2 bytes store the total length in big-endian format. After the header, we copy the NPDU into the frame, right after byte 4, assuming we actually have NPDU data to send. At this point, what we have in the output buffer is a complete BVLC frame, fully encoded and ready to send over UDP port 47808. Finally, the function returns the total number of bytes encoded, and so the data link layer knows exactly how many bytes to transmit. This completes the wrapping part of BACnet over BVLL. Alright, so at this point, we've completed the entire data link layer for BACnet over IPv4. That includes handling the BVLC header and sending and receiving BACnet IP packets using the W5500 Ethernet chip. Now that the data link layer is fully in place, we can move up one level in the stack. In this next part of video, we're going to start building the NPDU layer. This is where routing, version control, and network level flags come into play. It's the bridge between BACnet's transport layer and the application layer above. Let's dive in. Alright, now that we're moving into the NPDU layer, Let's take a look at how we actually process an incoming NPDU packet. So here we have the function BACnet NPDU receive handler. This function is responsible for taking raw NPDU data that we just received from the data link layer, decoding it, and then deciding whether it should be handled at the network layer or forwarded up to the APDU layer. Let's walk through it. First, we do some basic defensive checks. If the NPDU pointer is null, or the length is 0, we simply return there's nothing valid to process. Next, we decode the NPDU header. We call BACnet NPDU decode, which fills in an NPDU info structure. If the header can't be decoded, or the offset is invalid, we bail out immediately. Now, here's where the NPDU layer becomes meaningful. If this packet contains a network layer message, for example, who is router, I am router, or a reject message to network, we branch based on the message type. These messages are used for BACnet routing across multiple networks. At this stage, we're just stubbing them out, but this is where you'd implement router discovery or forwarding logic. And notice, network layer messages do not go up to the APDU layer. They are consumed at the NPDU level and returned. If the packet is not a network layer message, then what we have is a regular application packet. So we calculate the APDU pointer using the decoded offset, subtract the header length, and forward the remaining bytes to BACnet APDU receive handler. This hands control off to the next layer of the stack, where we process services like who is, I am, read property, write property, and so on. Now let's break down how we decode an NPDU packet. This function is called BACnet NPDU decode, and its job is to parse the NPDU header, extract routing information, and return the offset where the APDU data starts. First, we check for invalid inputs. If the buffer is null, the struct pointer is null, or we don't have at least 2 bytes, we return 0 and stop. There's simply not enough data to decode. We also reset the NPDU info structure to make sure it's clean before we fill it. Next, we decode the NPDU version. BACnet IP uses version 1, so if the value isn't 01, we return 0 and treat it as invalid. Then, we read the control byte. This byte tells us how to interpret the rest of the packet. From this 1 byte, we determine several flags: whether this packet is a network message, whether destination addressing is included, whether source addressing is included, and whether the sender expects a reply. These flags decide which fields come next. If the destination address is present, we parse destination network number, MAC length, and copy the destination MAC address if it exists. We also validate buffer boundaries to avoid overflow. If the source address is present, we do the exact same thing. Read the network number, length, copy the MAC address, and update the offset. After addressing, we decode the hop count, which is required when routing across multiple BACnet networks. This field appears only when destination information is included. Now, if the packet is a network layer message, we read the message type byte and store a pointer to the remaining message data. We return the offset directly because network messages do not contain APDU payloads. And if it's not a network message, then the offset we return points to the APDU, meaning the packet should continue up the stack to the application layer. Now, let's move on to the function BACnet NPDU transmit. This function constructs a full NPDU frame by adding the NPDU header in front of the APDU payload, and then sends it down to the data link layer for transmission. We begin with a safety check. The function returns immediately if the destination address NPDU info, or PDU buffer is invalid, or if the APDU length is 0. This prevents invalid memory access and ensures we only process valid frames. Next, we encode the NPDU header. A temporary buffer is allocated on the stack, and the function BACnet NPDU header encode writes the encoded header into this buffer. If header encoding fails, the function stops here. After the header is ready, we shift the APDU payload forward in memory. We use memove to handle overlapping memory regions safely. This creates space at the beginning of the buffer for the NPDU header. Then, we copy the NPDU header into the final PDU buffer. At this point, the buffer structure becomes NPDU header, followed by APDU payload. We compute the final PDU length by adding the header length and the APDU length together. Finally, the completed NPDU is passed to the data link layer using the function BACnet datalink send NPDU. This is where actual physical transmission happens. For example, over BACnet IP using UDP. In summary, this function takes an APDU, prepends a fully encoded NPDU header, calculates the final packet length, and sends it to the data link layer for delivery. Now let's break down the function BACnet NPDU header encode. This function builds the NPDU header and writes it into a caller-provided buffer. It returns the number of bytes written, which is later used to prepend the header to the APDU. We start with a parameter validation check. If the buffer is null, the NPDU structure is null, or the buffer is too small to hold even the version and control fields, we return 0 and stop immediately. Next, we write the protocol version. For BACnet, this value is always 1. This identifies the NPDU as a BACnet version 1 packet. Then we build the control byte. This field contains several bit flags that describe how the packet should be routed. For example, setting the destination flag means DNET and DADR fields are present. Setting the source flag means SNET and solder fields are present. Data expecting reply indicates the sender wants a response. And if the packet is a network layer message, the control byte will include the network flag. Finally, the priority is encoded in the lowest 2 bits. If a destination address is specified, we encode DNET, DLEN, and the destination MAC address. After that, we append the hop count, which defines how many routers the packet may traverse before being dropped. If a source address is specified, we follow the same format, SNET, SLEN, and the source MAC address. If the NPDU represents a network layer message, we write the network message type and optionally append additional message data. This includes messages such as who is router or I am router. At the end of the function, we return the number of bytes encoded into the buffer. This offset tells the caller where the APDU portion should begin. In summary, BACnet NPDU header encode constructs a standards-compliant NPDU header based on addressing flags, routing information, and network message type. The returned offset indicates where the next protocol layer should write its payload. So now that we've handled the NPDU layer, it's time to move up to the APDU layer. In the NPDU, if a BACnet message is not a network layer message, we pass it up to the APDU layer by calling functions like BACnet APDU receive handler. This is where the actual application logic lives. Processing services like who is, I am, read property, and write property. Let's dive in and see how the APDU layer decodes and handles these messages. Now we're in the APDU layer, where BACnet application messages are processed. The function BACnet APDU receive handler takes the APDU payload from the NPDU layer and the source address. It starts by reading the PDU type from the first byte. The upper 4 bits indicate the type of message, like confirmed service, unconfirmed service, acknowledgement, error, reject, or abort. Then, it routes the message to the appropriate handler. Unconfirmed service requests go to handle unconfirmed service request. Other types, like confirmed requests or ACKs, have their own handlers, which can be implemented as needed. Unknown or unsupported PDU types are ignored. In short, this function forwards APDU messages to the right service handler so the application layer can process BACnet commands and responses. To send data on the application layer, we have the function BACnet APDU transmit. First, it takes the APDU buffer from the application layer and performs basic validation, including the destination address, the data pointer, and the APDU length. If any of these are invalid, the function simply returns and nothing is sent. Then, it checks the APDU type to determine whether the message expects a reply. A confirmed service request will set a flag to track the response, while unconfirmed messages do not require a reply. Next, it determines how the packet will be delivered. It can be unicast to a specific device, or broadcast across the network. A MAC value of FF indicates a local broadcast. After that, it prepares the NPDU information, including hop count, destination network, and MAC address. These values define how the packet is routed through the BACnet network. Finally, it passes the APDU along with all NPDU metadata to BACnet NPDU transmit, which encodes the final frame and sends it out over BACnet IP. And that wraps up this video. In this session, we completed the data link layer for BACnet IP version 4 using the W5500 and fully implemented BACnet BVLC. At the network layer, we built the BACnet NPDU module, and at the application layer, we completed the BACnet APDU module. With the APDU module in place, our device can now create and process full BACnet APDU messages, which are then encapsulated by NPDU and sent through the data link to the network. In the next video, we will start building the BACnet confirmed service and unconfirmed service modules, and then move up to the application layer to implement the first BACnet services required for device discovery, specifically who is and I am. Thanks for watching. If you liked it, hit like, subscribe, and turn on the bell for notifications. See you in the next